Retrieval-Augmented Generation, or RAG. It's the backbone of how modern AI goes beyond memory to reason with facts, stay up to date, and power real-world applications. But here's the truth. Most people only scratch the surface. In interview, what really sets you apart is not just knowing what RAG is, but understanding how it works, where it fails, and how it's evolving. So in this video, I've put together the 100 most important RAG interview questions, from fundamentals to advanced architectures, from compliance and evaluation to the future of multimodal retrieval. By the end, you won't just be ready for an interview. You'll think like the people building the next generation of AI systems. Let's dive in and master RAG interview questions. What is Retrieval-Augmented Generation, or RAG, and why was it introduced? RAG, or Retrieval-Augmented Generation, is a framework that combines a large language model with an external retriever. Instead of relying only on the model's pre-trained knowledge, RAG retrieves relevant information from external sources like databases, documents, or search indexes, and injects that into the model before generation. This approach was introduced because LLMs alone have limitations. They can hallucinate, they have knowledge cutoffs, and they can't access private or enterprise-specific data. By adding retrieval, RAG makes responses more accurate, up-to-date, and grounded in real evidence. It's especially powerful in enterprise settings, where models need to reason over sensitive data, like company emails or medical records, without retraining the LLM itself. In short, RAG turns LLMs from good generalists into reliable domain experts. How does RAG differ from a standalone LLM? A standalone LLM works only from what it learned during training. That means its knowledge stops at a certain point, and sometimes it makes things up, which we call hallucinations. RAG, or Retrieval-Augmented Generation, adds an extra step. Before answering, it searches external sources, like company documents, databases, or the web, and then feeds that information into the model. This makes the response more accurate, up-to-date, and grounded in real data. The key difference is that an LLM alone is like answering only from memory, while RAG is like checking your notes or a library before giving the answer. That's why RAG is widely used in enterprises where accuracy and fresh knowledge really matter. Can you explain the two main components of RAG, retrieval and generation? RAG has two main parts, retrieval and generation. The retrieval part is like a search engine. It finds the most relevant pieces of information from external sources, such as databases, documents, or knowledge bases. Then comes the generation part, which is the large language model itself. The LLM takes both the user's question and the retrieved information and uses them together to create a clear and grounded answer. Retrieval ensures the model has the right context, while generation ensures the response is natural, fluent, and well-structured. In simple terms, retrieval brings the facts and generation explains them. That teamwork is what makes RAG much more accurate and useful than a model alone. What are the limitations of traditional LLMs that RAG solves? Traditional LLMs have three big limitations. First, they have a knowledge cutoff. They can't access information beyond their training data. Second, they often hallucinate, which means they confidently give wrong or made-up answers. And third, they can't easily work with private or domain-specific data, like company files or medical records, unless they're retrained, which is costly. RAG was introduced to solve these problems. By adding retrieval from external sources, RAG gives the model fresh, accurate, and domain-specific context. This makes the responses more trustworthy and directly useful in real-world applications, like enterprise search, customer support, or healthcare. In short, RAG fixes what standalone LLMs miss. Describe the basic RAG pipeline step by step. The RAG pipeline works in a few simple steps. First, the user asks a question. That question is turned into embeddings, basically numerical representations of meaning. Second, those embeddings are used to search a knowledge source, like a vector database or document store, to retrieve the most relevant chunks of information. Third, the retrieved context is combined with the original question and passed to the language model. Finally, the LLM uses both the query and the supporting documents to generate a grounded, natural answer. In short, query, retrieve, combine, generate. This simple flow is what makes RAG accurate and reliable in practice. What is a vector database, and why is it critical in RAG? A vector database is a special type of database designed to store and search embeddings, which are numerical representations of text, images, or other data. In RAG, it plays a critical role because when a user asks a question, the system converts it into an embedding and then looks for the closest matches in the vector database. This allows the model to find semantically similar information, not just keyword matches. Without a vector database, retrieval would be slow and less accurate, especially with large collections of documents. In short, the vector database is the memory bank that makes RAG fast, scalable, and context-aware. How does retrieval quality impact final generation in RAG? Retrieval quality largely determines answer quality in RAG. If you fetch the right, precise chunks, the LLM can produce accurate, grounded responses. If retrieval brings noisy, outdated, or off-topic content, the model may still sound fluent, but will drift or hallucinate. Three things matter most: good chunking, so facts aren't split awkwardly; strong retrievers and re-rankers, to surface the best passages; and relevance filtering, to drop weak matches. Think of it like cooking. Great ingredients make a great dish. Bad ingredients can't be fixed by fancy plating. In practice, teams often see bigger gains by improving retrieval than by swapping LLMs. Compare dense versus sparse retrieval methods in the context of RAG. In RAG, there are two main retrieval methods: sparse and dense. Sparse retrieval, like BM25, relies on exact keyword matches. It's simple and fast, but often misses meaning if the wording is different. Dense retrieval, on the other hand, uses embeddings to capture the semantic meaning of text. This allows it to find results even when the words don't match exactly, like connecting car with automobile. Dense methods are more powerful for understanding context, but they require vector databases and more compute. In practice, many RAG systems combine both, sparse for precision and dense for semantic coverage, to improve reliability. How do embeddings enable semantic retrieval in RAG? Embeddings are numerical vectors that capture the meaning of text. In RAG, they allow the system to compare the user's question with stored documents based on meaning, not just exact words. For example, if you ask about heart attacks, embeddings can also match content about cardiac arrest, even though the wording is different. This semantic matching is what makes retrieval powerful. It understands context and similarity at a deeper level. Without embeddings, retrieval would be limited to keyword search. With them, RAG can connect questions to the right knowledge more flexibly and accurately. What is grounding, and how does RAG ensure grounded responses? Grounding means making sure the model's answers are based on real, verifiable information instead of just what it remembers. In RAG, grounding happens because the system retrieves facts from trusted sources, like company documents, databases, or knowledge bases, and feeds them into the model along with the question. The LLM then generates its response using that retrieved context. This way, the answer isn't only fluent, but also backed by actual data. Grounding reduces hallucinations, improves trust, and makes the output something users can rely on, especially in enterprise or sensitive domains. What are the main differences between naive RAG and advanced RAG? Naive RAG is the simplest form. It just takes the user's query, retrieves the top documents, and passes them to the LLM. It works, but often the retrieval isn't perfect, and irrelevant or noisy text can hurt the final answer. Advanced RAG improves this by adding smarter steps like query rewriting, re-ranking retrieved results, filtering low-quality chunks, or even doing multiple retrieval rounds. This makes the context much more accurate and tailored before the model generates. In short, naive RAG is retrieve and generate, while advanced RAG adds intelligence in between to boost quality and reliability. Explain corrective RAG, and how it improves over standard RAG. Corrective RAG, or CRAG, is an advanced version of RAG that adds an extra validation step. In standard RAG, the model uses whatever documents are retrieved, even if some are irrelevant. CRAG fixes this by checking the quality of the retrieved results using filters, re-rankers, or even the LLM itself to decide which chunks are useful and which should be discarded. By correcting poor retrieval before generation, CRAG reduces noise, lowers hallucinations, and produces more accurate, trustworthy answers. In simple terms, it doesn't just retrieve, it double-checks the retrieval before letting the model generate. What is speculative RAG, and when would you use it? Speculative RAG is a technique where instead of relying on a single retrieval, the system explores multiple possible retrievals in parallel. Think of it as testing different what-if contexts for the same query. The model then evaluates or merges these candidate results to produce a stronger final answer. This approach is useful when the question is ambiguous, broad, or has multiple valid angles. For example, in research, legal, or medical queries, where missing one perspective could hurt accuracy. In short, speculative RAG improves coverage by retrieving and considering several possibilities, rather than betting on just one. How does Fusion RAG combine multiple retrievers, and what's the benefit? Fusion RAG works by combining results from multiple retrievers instead of relying on just one. For example, it might use a sparse retriever like BM25 for keyword matches, and a dense retriever using embeddings for semantic matches. Then it merges or re-ranks the combined results before passing them to the LLM. The benefit is better balance. Sparse methods catch precise keywords, while dense methods capture meaning. Together, they cover more ground and reduce the chance of missing important context. Fusion RAG is especially useful in domains where both exact terms and broader concepts matter, like legal or technical documents. Describe self-RAG and how self-reflection enhances retrieval accuracy. Self-RAG is a version of RAG where the language model reflects on its own retrievals. Instead of blindly using whatever documents come back, the model reviews them, checks if they truly answer the question, and can even ask for a better retrieval if needed. This self-reflection loop improves accuracy by filtering out irrelevant chunks and guiding retrieval toward more useful context. The result is fewer hallucinations and more precise answers. In simple terms, self-RAG lets the model act like a student, double-checking their sources before writing the final response. What is agentic RAG, and how does it integrate planning and retrieval? Agentic RAG is when RAG is combined with agent-like behavior. Instead of just retrieving once and generating an answer, the model can plan multiple steps, refine its query, retrieve again, and even decide which tools or data sources to use. This planning and retrieval loop makes it more interactive and flexible. For example, if the first retrieval is weak, an agentic RAG system can rewrite the question and try again, just like a researcher would. This approach is powerful for complex or multi-step tasks because it doesn't settle for the first result. It actively reasons about how to get the best context. How does Graph RAG differ from traditional RAG? Graph RAG is different from traditional RAG because instead of retrieving plain text chunks, it retrieves information from a knowledge graph. A knowledge graph stores data as entities and relationships, like Alice works at Microsoft or diabetes is linked to high blood sugar. This structure makes it easier to answer complex, multi-hop questions that need reasoning across connections. For example, in healthcare, Graph RAG can link symptoms, diseases, treatments in a way plain text retrieval cannot. In short, traditional RAG finds text, while Graph RAG finds facts and relationships, making the answers more structured and explainable. What role does HyDe, hypothetical document embedding, play in RAG? HyDe, or hypothetical document embedding, is a clever trick used in RAG to improve retrieval. Instead of sending the raw user query to the retriever, the LLM first generates a short, hypothetical answer, or draft document to that query. That draft is then converted into embeddings and used to search the database. The idea is that the generated text captures the intent of the question more fully than just the query alone, so retrieval finds more relevant documents. This approach is especially useful for vague or complex queries, where a simple keyword or embedding search might miss the right context. Explain adaptive RAG and how it dynamically changes retrieval. Adaptive RAG is a smarter version of RAG that adjusts how it retrieves information based on the question or the context. Instead of always retrieving a fixed number of documents in the same way, it can decide to fetch more, fewer, or different kinds of sources depending on what's needed. For example, a simple factual question might only need one reliable document, while a broad research query may require pulling from multiple databases. This dynamic behavior makes adaptive RAG more efficient and accurate because it tailors retrieval to the situation instead of using a one-size-fits-all approach. What are the differences between modular RAG and end-to-end RAG pipelines? In a modular RAG pipeline, each step like embedding generation, retrieval, re-ranking, and answer generation is handled separately with clear components. This makes it easier to swap, tune, or improve parts without changing the whole system. In contrast, an end-to-end RAG pipeline tries to train or optimize everything together in one flow. That can give better performance, but is harder to control and debug. Modular RAG is flexible and practical for real-world use, while end-to-end RAG is more research-focused, aiming for maximum integration and accuracy. In short, modular equals plug-and-play, end-to-end equals all-in-one. How do you chunk documents for retrieval and RAG, and why does it matter? Chunking means breaking long documents into smaller pieces so they can be stored in a vector database for retrieval. This matters because LLMs have a limited context window and can't handle very long texts at once. If chunks are too big, important details may get cut off or skipped. If they're too small, retrieval may return fragments that lose meaning. The goal is to find a balance, usually a few hundred tokens per chunk, with some overlap, so each piece is meaningful and searchable. Good chunking improves retrieval accuracy, reduces noise, and helps the model generate more grounded answers. What are the trade-offs between small versus large chunk sizes in retrieval? Chunk size is a balancing act in RAG. Small chunks give you very precise retrieval since each piece focuses on a single idea, but they can also lose context, and the system may pull too many fragments that overwhelm the model. Large chunks preserve more context, like whole sections of a document, but they risk pulling in extra noise or irrelevant details. Small chunks equals precision, but risk of fragmentation. Large chunks equals context, but risk of dilution. In practice, teams often use medium-sized chunks with slight overlaps to get the best of both worlds. How does re-ranking improve retrieval quality in RAG? Re-ranking is the step where we take the initial set of retrieved documents and reorder them based on how relevant they truly are to the question. The first retriever might bring back 50 results, but not all are equally useful. A re-ranker, often a smaller model or even the LLM itself, scores these results and pushes the best matches to the top. This improves the quality of context given to the LLM, reducing noise and making the final answer more accurate. In simple terms, retrieval gets the candidates, and re-ranking makes sure the right ones are chosen first. Explain how embeddings are trained for domain-specific RAG. Embeddings are the backbone of retrieval, and for domain-specific RAG, they need to capture the language of that field. Instead of using only general-purpose embeddings, teams can fine-tune them on domain data, like medical records, legal documents, or financial reports. This way, the embeddings learn the special terms, abbreviations, and context of that domain, making retrieval much more accurate. For example, in healthcare, MI should be understood as myocardial infarction, not Michigan. Training or fine-tuning embeddings on domain data ensures the system retrieves the right chunks, which leads to more reliable answers from the RAG pipeline. What are the advantages and risks of using approximate nearest neighbor, ANN, search in RAG? Approximate nearest neighbor, or ANN, is used in RAG to quickly find similar embeddings from a large database. The big advantage is speed. It makes retrieval scalable, even when you have millions of documents. Without ANN, exact search would be too slow for real-time applications. But the trade-off is accuracy. Since it's approximate, sometimes the results may not be the true closest matches, which can affect answer quality. In practice, ANN works well because the small drop in accuracy is usually worth the huge gain in performance, but it's important to tune it carefully for critical use cases. How would you handle long documents in a RAG pipeline? Handling long documents in RAG usually comes down to smart chunking and indexing. Instead of storing the whole document as one piece, you break it into smaller, meaningful sections with some overlap so context isn't lost. You can also use hierarchical retrieval. First identify the right section of a document, then retrieve chunks from within it. Another approach is summarization, where you store condensed versions of long text alongside the original. These methods keep retrieval efficient, ensure the LLM isn't overloaded, and still give it enough context to generate accurate, grounded answers. What role does prompt engineering play in RAG effectiveness? Prompt engineering plays a key role in RAG because it controls how the retrieved context and the user's question are presented to the LLM. A well-designed prompt tells the model to focus on the retrieved documents, cite them if needed, and avoid adding extra information. Without clear prompts, the model may ignore the context or still hallucinate. For example, adding instructions like answer only based on the provided documents or formatting the retrieved text clearly can improve reliability. In short, good prompt design makes sure the LLM uses the retrieved knowledge effectively instead of drifting away from it. How do you evaluate retrieval quality separately from generation quality? To evaluate retrieval quality separately, we check how relevant the retrieved documents are before the LLM even generates an answer. Common methods include precision and recall, measuring how many of the retrieved chunks are actually useful compared to what should have been retrieved. Another approach is using relevance judgments, where humans or smaller models label whether the documents match the query. You can also look at metrics like mean average precision, MAP, or NDCG, which score ranking quality. By testing retrieval on its own, we can fine-tune embeddings, chunking, and re-ranking, ensuring the generator gets the best possible context. What metrics are used to evaluate the performance of a RAG system? Evaluating a RAG system usually involves two layers of metrics. For retrieval, we use metrics like precision, recall, mean average precision, EMAP, or NDCG to see how well the right documents were pulled. For generation, we use metrics like Rouge, Blue, or BERT score to compare the output against reference answers. And more recently, faithfulness or grounding scores to check if the response is truly based on retrieved context. In real-world settings, human evaluation, checking accuracy, helpfulness, and trustworthiness is also very important. Together, these metrics show if RAG is both retrieving the right data and generating the right answers. How do you design caching strategies for RAG to reduce cost per latency? Caching in RAG helps cut down both cost and latency by reusing results instead of repeating the same work. One strategy is query-level caching. If the same or very similar query comes again, return the stored retrieval results instead of searching the database again. Another is embedding caching. Store the vector representations so you don't recompute them each time. You can also cache common responses from the LLM for FAQs or repeated tasks. The challenge is balancing freshness with speed, since cached results may get outdated if the underlying data changes. Done right, caching makes RAG systems faster and cheaper. Give an example of how RAG is used in enterprise search. In enterprise search, RAG is used to make company knowledge easily accessible. For example, instead of employees digging through SharePoint, emails, or PDFs, they can just ask a natural question like, "What's our policy on remote work?" The system retrieves the most relevant documents from internal sources, and then the LLM generates a clear, summarized answer. This saves time, reduces confusion, and ensures people get accurate information quickly. Microsoft 365 Copilot is a real-world example. It uses RAG to ground answers in Microsoft Graph data like Teams chats, Word files, and Outlook emails. How does RAG power Microsoft 365 Copilot, Word, Excel, Outlook? RAG is at the core of Microsoft 365 Copilot. When you ask something in Word, Excel, or Outlook, the system doesn't just rely on the model's memory. It retrieves context from your organization's data inside Microsoft Graph, like emails, documents, Teams chats, and calendars. That information is then fed into the LLM to generate answers that are both accurate and specific to your work. For example, in Outlook, it can draft a reply using details from a related document, or in Excel, it can summarize trends using your company data. RAG makes Copilot grounded, trustworthy, and enterprise-ready. How can RAG be applied in healthcare for clinical decision support? In healthcare, RAG can support doctors by retrieving medical knowledge and patient data to assist in decision-making. For example, If a physician asks about treatment options for a condition, the system can pull the latest research papers, clinical guidelines, and even the patient's electronic health record. The LLM then generates a clear, context-aware summary or recommendation. This helps reduce errors, saves time, and ensures care is based on up-to-date evidence. Importantly, since healthcare is sensitive, RAG also allows grounding responses in trusted compliant sources rather than relying only on the model's training data. What are some common use cases of RAG in legal tech? In legal tech, RAG is very powerful because lawyers work with massive amounts of documents. Common use cases include contract review, where RAG retrieves specific clauses and the LLM explains them in plain language. Legal research, where it pulls relevant case law or statutes to answer a query. And compliance checks, where it grounds responses in regulatory documents. For example, instead of reading through hundreds of pages, a lawyer could ask, "What does this contract say about termination rights?" And RAG will fetch the exact section and generate a clear summary. This saves time and reduces risk of oversight. How does RAG improve chatbots compared to retrieval-only or generation-only systems? Traditional chatbots that only retrieve documents can feel rigid. They just show text snippets without real conversation. On the other hand, generation-only chatbots can sound natural, but may hallucinate or give wrong answers. RAG combines the best of both. It retrieves accurate information from trusted sources and then uses the LLM to explain it in a natural, conversational way. This makes the chatbot both reliable and engaging. For example, in customer support, a RAG-powered bot can pull the exact policy from the knowledge base and then summarize it clearly for the user, instead of copying text or making things up. Can RAG be used for code generation? If yes, how? Yes, RAG can be very useful for code generation. Instead of relying only on the model's training data, RAG retrieves code snippets, documentation, or API references from trusted repositories. The LLM then uses this context to generate or adapt code. For example, if a developer asks, "How do I connect to Azure Storage in Python?" the retriever can pull the latest SDK examples, and the model can generate a working script using that context. This keeps the code accurate, up to date with libraries, and aligned with company-specific coding standards. In short, RAG grounds code generation in real documentation. How does RAG enable personalized recommendations in e-commerce? In e-commerce, RAG can power personalized recommendations by combining user data with product knowledge. For example, if a customer asks, "What's the best laptop for video editing under $1,000? The retriever can pull details from the product catalog, reviews, and specifications. The LLM then generates a tailored answer, highlighting models that match both the budget and the use case. Because retrieval can include customer history or preferences, the recommendations feel more personal. This approach improves the shopping experience by making suggestions accurate, relevant, and conversational instead of just showing a list of products. What role does RAG play in customer support copilots? RAG is a game changer for customer support copilots because it grounds answers in a company's real knowledge base. When a support agent or customer asks a question, the system retrieves policies, manuals, or past ticket solutions, and the LLM explains them in simple, conversational language. For example, instead of scrolling through a 50-page troubleshooting guide, the copilot can instantly summarize the exact fix for a product issue. This saves agents time, improves first response accuracy, and gives customers faster, more reliable help. In short, RAG makes customer support copilots both smart and trustworthy. How does RAG enhance multilingual applications? RAG enhances multilingual applications by retrieving information in any language and letting the LLM translate or generate responses in the user's preferred language. For example, if a company's documents are in English but a customer asks in Spanish, the retriever can still find the English content, and the LLM can deliver the answer in Spanish. This makes knowledge universally accessible without needing to duplicate or translate all documents ahead of time. It's especially valuable for global businesses, where users speak different languages but need consistent, accurate answers grounded in the same source material. Compare the use of RAG in consumer AI apps versus enterprise AI solutions. In consumer AI apps, RAG is often used to give users better information from public sources, like retrieving news articles, Wikipedia entries, or product reviews, so answers feel fresh and relevant. In enterprise AI solutions, the focus is different. RAG retrieves from private, internal data such as company documents, emails, or policies. This makes it more about security, compliance, and accuracy in a business context. In short, consumer RAG is about convenience and up-to-date knowledge, while enterprise RAG is about trust, grounding in sensitive data, and improving productivity inside organizations. What are the most common failure points in a RAG system? The most common failure points in a RAG system usually come from three areas. First is poor retrieval. If the system pulls irrelevant or incomplete documents, the final answer will be weak no matter how good the LLM is. Second is bad chunking or indexing, where important context gets lost or split incorrectly. Third is generation drift, where the model ignores the retrieved context and hallucinates its own answer. Other issues include latency when dealing with very large databases and data privacy risks if sensitive information is not handled carefully. Fixing retrieval quality usually solves most of these failures. How does RAG handle hallucinations? And what cases can still fail? RAG reduces hallucinations by grounding the LLM's answers in retrieved documents. Instead of relying only on memory, the model gets real evidence from trusted sources, which keeps it closer to the facts. However, it's not a perfect fix. If the retrieval step pulls irrelevant or low-quality documents, the model may still hallucinate or give misleading answers. Also, if the knowledge simply doesn't exist in the database, the LLM might try to fill the gap by making something up. So while RAG lowers the risk of hallucinations, careful retrieval design and source quality are still critical. What happens if retrieval returns irrelevant or noisy documents? If retrieval returns irrelevant or noisy documents, the LLM will still try to use them, which can lead to wrong or confusing answers. Since the model is designed to generate fluent text, it may confidently present information that doesn't actually address the question. This is one of the biggest weaknesses of RAG. Bad input leads to bad output. To reduce this risk, systems often use re-rankers, filters, or even self-checking steps like corrective RAG to make sure only the most relevant chunks are passed to the model. In short, poor retrieval directly harms answer quality. How do you prevent data leakage in enterprise RAG systems? Preventing data leakage in enterprise RAG systems is about controlling what data gets retrieved and exposed. First, you enforce strict access controls, so users only retrieve documents they are authorized to see. Second, you secure the vector database with encryption and audit logging. Third, you filter or mask sensitive fields like personal information before indexing. Some systems also add guardrails in the generation step, reminding the model to avoid exposing confidential content. Together, these measures ensure that while RAG provides powerful search and answers, it doesn't leak private or restricted company data to the wrong users. What ethical challenges exist in using RAG for sensitive domains like finance or healthcare? In sensitive domains like finance or healthcare, the main ethical challenge with RAG is trust. If retrieval pulls outdated or biased documents, the model may give harmful or misleading advice. There's also the risk of exposing private or regulated data, like patient records or financial transactions, if access controls aren't strict. Another challenge is accountability. Users may assume the AI's answers are always correct, even if they're based on limited context. That's why in these domains, RAG must be built with transparency, strong data governance, and clear disclaimers, so people know the system supports decisions but doesn't replace experts. What is dynamic RAG, and how does it differ from standard pipelines? Dynamic RAG is a more flexible version of RAG, where the retrieval process adapts while the model is generating an answer. In a standard RAG pipeline, retrieval happens once at the start, and the model uses whatever context it gets. Dynamic RAG, on the other hand, can notice gaps in information during generation and trigger new retrievals to fill them. This makes it better for complex or multi-step queries where one round of retrieval isn't enough. In short, standard RAG is static, retrieve once, while dynamic RAG is adaptive, retrieving as needed throughout the reasoning process. Explain parametric RAG and how it integrates retrieved data deeper into the model. Parametric RAG takes the idea of RAG a step further by blending external knowledge more deeply into the model. In normal RAG, retrieved documents are added to the prompt, so the model sees them only as extra context. In parametric RAG, the retrieved knowledge is injected into the model's internal layers or parameters, making it part of the reasoning process rather than just an add-on. This can reduce token overhead, improve accuracy, and make the model feel like it has learned the external data without full retraining. It's an emerging approach to make RAG more efficient and tightly integrated. What is typed RAG, and why is it important for non-factoid Q&A? Typed RAG is a newer approach where a question is broken down into different types or aspects, such as factual details, reasoning steps, or style requirements. Each type is matched with its own retrieval strategy, so the system can pull the right kind of information for each part. This is especially important for non-factoid Q&A questions that need more than a simple fact, like explanations, comparisons, or analysis. By tailoring retrieval to the type of information needed, typed RAG makes the answers more complete and balanced, instead of just returning raw facts. How is multimodal RAG, MRAG, evolving, and what are its applications? Multimodal RAG, or MRAG, extends RAG beyond text by retrieving from multiple data types like images, audio, and video in addition to documents. For example, in healthcare, it could pull both medical reports and X-ray images to help answer a diagnostic question. In e-commerce, it might combine product descriptions with customer photos or reviews. The evolution of MRAG is making AI assistants more powerful because they can ground their answers in richer, real-world information, not just text. This opens up new applications in education, media, and enterprise, where knowledge often spans many formats. Where do you see RAG heading in the next 3 to 5 years in enterprise AI? In the next 3 to 5 years, RAG will become the backbone of enterprise AI. Today, it mostly retrieves text, but it's moving toward multimodal retrieval, combining documents, charts, images, and even video. We'll also see tighter integration with agents, where RAG doesn't just provide context but helps the system plan, reason, and act. Another big shift will be toward real-time, dynamic retrieval that adapts as conversations unfold. Finally, enterprises will demand stronger governance, secure, compliant RAG pipelines that protect sensitive data while scaling across the business. In short, RAG is evolving from an add-on to being the core of trustworthy, domain-specific AI. What are the fundamental challenges solved by classic ERAG versus standalone LLMs? Classic RAG solves 3 big challenges that standalone LLMs face. First, knowledge cutoff. LLMs can't access new information after training, while RAG pulls from live data sources. Second, hallucinations. LLMs may make up facts, but RAG grounds answers in retrieved documents. Third, domain knowledge. LLMs don't know enterprise-specific data unless retrained, but RAG can access company files directly. By combining retrieval with generation, classic RAG makes AI more accurate, up-to-date, and business-ready without the cost of retraining models. That's why it became the foundation for enterprise copilots like Microsoft 365 Copilot. Can you walk us through the classic RAG pipeline, step by step? The classic RAG pipeline has 4 main steps. First, the user asks a question, which is converted into an embedding, a vector representation of its meaning. Second, that embedding is used to search a vector database to retrieve the most relevant chunks of information. Third, the system combines the original question with the retrieved documents to form a prompt. Finally, the large language model generates an answer based on both the question and the supporting evidence. In short, query, retrieve, combine, generate. This simple flow makes RAG powerful and reliable compared to a standalone LLM. In real-world deployments, where do you see classic RAG failing most often? Classic RAG usually fails in 3 common areas. First is poor retrieval. If the database returns irrelevant or incomplete chunks, the final answer suffers. Second is bad document chunking, where context is cut in the wrong places, leading to confusing or fragmented results. Third is generation drift, where the LLM ignores the retrieved context and falls back on its own memory, which can cause hallucinations. These issues show up often in enterprise deployments with large, messy knowledge bases. Fixing retrieval quality and prompt design usually solves most of these failures. What are key performance indicators you track for classic RAG models? For classic RAG, we usually track 4 key performance indicators. First is retrieval precision. How many of the retrieved chunks are truly relevant? Second is grounding or faithfulness, whether the generated answer actually uses the retrieved evidence. Third is latency, since users expect fast responses even with retrieval in the loop. And fourth is user satisfaction or task success, often measured through feedback or accuracy checks. Together, these KPIs show if RAG is not only retrieving the right data, but also generating useful, timely, and trusted answers. How do updates to knowledge bases affect the reliability of classic RAG systems? Knowledge base updates can make or break a RAG system. If the knowledge base is kept fresh, RAG becomes highly reliable because every query is grounded in the latest information. But if it's outdated or inconsistent, the system may give answers that are no longer valid, even if the retrieval works correctly. The reliability also depends on how often embeddings are regenerated after updates. If chunks aren't re-indexed, new data won't be searchable. In short, RAG is only as good as the knowledge base behind it, so maintaining and syncing that data is critical. What's the simplest way to start prototyping with RAG for business search? The simplest way is to start small with a vector database and an LLM. First, take a few key business documents, like policies, FAQs, or product manuals, and break them into chunks. Next, generate embeddings for those chunks using an embedding model and store them in a vector database such as Pinecone, Weaviate, or Azure Cognitive Search. Then, when a user asks a question, retrieve the most relevant chunks and feed them into an LLM like GPT. This quick setup can be done in days and gives an immediate proof of concept for business search without heavy infrastructure. How do you handle hallucinations in classic RAG architecture? Hallucinations in classic RAG are reduced by grounding the model's answers in retrieved documents, but they can still happen if retrieval isn't strong. To handle this, we add clear prompt instructions like answer only from the provided context. We also use re-rankers to filter out irrelevant chunks before passing them to the LLM. In some cases, adding citations or highlighting the source helps the model stay faithful. For sensitive domains, guardrails or verification steps can double-check the output. In short, strong retrieval plus good prompting are the best ways to control hallucinations in RAG. What's a good example of classic RAG in everyday consumer tech? A simple example of classic RAG in consumer tech is smart assistants like Alexa or Google Assistant when they answer factual questions. Instead of relying only on their built-in model, they often retrieve information from sources like Wikipedia or news sites, then generate a spoken response. Another example is customer support chatbots on e-commerce sites, which retrieve answers from FAQs or product manuals and present them in natural language. These use cases show how classic RAG blends search with language generation to give users clear, grounded answers in everyday apps. How is branch selection implemented for large enterprise settings? In large enterprises, branch selection means deciding which knowledge silo to search before retrieval. This is usually implemented with a routing step. The system classifies the query, then directs it to the right branch, like HR documents, legal contracts, or product manuals. Technically, this can be done using intent classifiers, metadata tags, or even a lightweight LLM that chooses the branch. Once the branch is selected, retrieval happens only within that silo, making results more accurate and efficient. This setup avoids searching across millions of irrelevant documents and keeps responses domain-specific. When is introducing branch routing overkill in a RAG system? Branch routing becomes overkill when the knowledge base is small or the queries don't clearly belong to separate categories. In such cases, adding a routing step just adds complexity, latency, and extra failure points without improving accuracy. For example, if a startup only has a few hundred documents, a single retrieval system can handle them easily. Branching makes more sense in very large enterprises with multiple silos of knowledge, but for smaller or simpler setups, a well-designed single RAG pipeline is usually faster and easier to maintain. In what ways does branch selection improve or harm retrieval precision? Branch selection can improve precision by narrowing the search space. If a query is routed directly to the right knowledge silo, retrieval brings back more relevant results and avoids noise from unrelated documents. But it can also harm precision if the routing is wrong. Sending a query to the wrong branch means the best documents are never even considered. So the quality of branch selection directly impacts retrieval performance. In short, good routing boosts precision, while poor routing can be worse than having no routing at all. Can you describe a scenario where branch drag changed business outcomes? One example is in a global bank with different departments like compliance, customer service, and investment research. Before branch drag, employees had to search across all documents, which often brought irrelevant results. After adding branch selection, queries were automatically routed. For instance, compliance questions only search regulatory documents. This cut down noise, sped up responses, and improved accuracy for staff. The outcome was faster decision-making, reduced compliance risk, and higher employee productivity. In this case, branch drag turned a messy, overwhelming search experience into a focused and reliable assistant. How do you maintain and update multiple knowledge silos for branch-based RAG? Maintaining multiple silos requires a strong content management process. Each branch, like HR, legal, or finance, needs its own pipeline for uploading documents, chunking them, generating embeddings, and updating the vector store. Automation helps here, so whenever a document is updated, the embeddings are refreshed automatically. Metadata tagging is also critical, so documents stay tied to the right branch. Regular audits ensure silos don't drift out of date. In short, the key is automated pipelines, metadata discipline, and periodic quality checks to keep each branch current and reliable. What testing strategies are used for branch routing effectiveness? To test branch routing, we usually run 3 checks. First is accuracy testing, where sample queries are labeled with the correct branch, and we see if the router makes the right choice. Second is A/B testing, comparing performance with and without routing to measure improvements in precision and latency. Third is error analysis, looking at misrouted queries to see if they came from unclear intent or poor metadata. Some teams also use user feedback loops, flagging when the wrong branch was chosen. Together, these strategies ensure branch routing actually improves results instead of adding mistakes. Describe a failure mode unique to branched RAG and how it was mitigated. A common branched RAG failure is router lockout. The query is routed to the wrong silo, say HR instead of legal, so the best documents are never searched. The model then answers confidently but incorrectly because it never saw the right evidence. We mitigated this with 3 steps. 1. A fallback global search if top answers in the chosen branch score below a relevance threshold. 2. Lightweight query rewriters that add missing keywords to improve routing. And 3. User-facing branch hints. Chips like try legal and product support so users can switch quickly. This combo cut misroutes and recovered accurate answers without heavy latency costs. What's the technical stack for implementing persistent memory in RAG? Persistent memory in RAG usually combines a vector database with a memory store. The vector database, like Pinecone, Weaviate, or Azure Cognitive Search, handles long-term storage of embeddings for documents. For session memory, you can use a key value store like Redis or a database like PostgreSQL to keep conversation history linked to the user. Middleware is added to decide what gets stored, important facts, user preferences, or past answers. Finally, orchestration tools like LangChain or Semantic Kernel manage how this memory is injected back into the prompt. Together, this stack gives RAG both long-term knowledge and user-specific memory. Can you share a time when memory-enhanced RAG significantly boosted user experience? A good example is in customer support copilots. Without memory, every time a customer returned, the system treated them as new, forcing them to repeat details. With memory-enhanced RAG, the assistant could recall the customer's past issues, preferences, or unresolved tickets. So if someone came back asking, "What's the update on my last order issue?" the system retrieved both the policy documents and the user's past interaction. This made the experience smoother, faster, and more personal. For the business, it also reduced handling time and improved customer satisfaction scores. How do you safeguard user privacy in memory-augmented systems? Safeguarding privacy in memory-augmented RAG starts with data minimization, only storing what's essential for improving the user experience. Next is encryption, both in transit and at rest, so sensitive details can't be leaked. Access control ensures that only the right users or services can see their memory. We also add retention policies, so old or irrelevant data is automatically deleted after a set time. Finally, transparency matters. Users should know what's stored and have the ability to clear their memory. These steps keep memory helpful without compromising privacy or compliance. What are the risks of accumulating stale info in RAG memory? The biggest risk with stale info in RAG memory is that the system may use outdated or incorrect context, leading to wrong answers. For example, if an old company policy remains in memory after being updated, the model could give advice that no longer applies. This not only frustrates users, but can also create compliance or legal issues. Stale memory also clutters retrieval, making it harder for the system to surface the most relevant facts. That's why memory needs regular refreshing, version control, and expiry rules to prevent outdated knowledge from sneaking into answers. When does session memory become counterproductive for information retrieval? Session memory becomes counterproductive when it starts to bias the system too heavily toward past conversations, even if they're no longer relevant. For example, if a user once asked about cloud storage, but later shifts to cloud security, the assistant may keep pulling storage-related context and miss the new focus. It can also overload prompts if too much history is injected, slowing responses and confusing the model. In short, memory is helpful for continuity, but if not managed carefully, it can trap the system in old context instead of adapting to the user's current need. Is there a maximum practical memory window for effective RAG performance? Yes, there is a practical limit. Even though modern LLMs have large context windows, stuffing too much memory into a prompt can actually hurt performance. Beyond a few thousand tokens, the model may lose focus, mix up details, or take longer to respond. The sweet spot is usually keeping only the most recent or most relevant memory snippets instead of the full history. Techniques like summarization and relevance filtering help shrink the memory window while keeping it useful. In practice, smaller, well-curated memory windows often work better than trying to remember everything. How do you decide which context to append to retrieved results? The key is relevance and usefulness. After retrieval, not all chunks are equally valuable, so we usually re-rank results and select the top ones that best match the query. We also look at diversity, choosing context that covers different angles instead of repeating the same point. Sometimes metadata like date, author, or source reliability helps decide which context to keep. Since prompt space is limited, it's better to append fewer high-quality chunks than overload the model. In short, append the context that is most relevant, diverse, and trustworthy for the question. Has adding context ever resulted in more hallucinations? How did you fix it? Yes, sometimes adding too much or low-quality context can actually confuse the model and increase hallucinations. For example, if irrelevant chunks are appended, the LLM may try to force them into the answer, mixing facts with noise. We fix this by improving re-ranking so only the most relevant context is passed, and by limiting the number of chunks to avoid overload. Another solution is prompt instruction, telling the model to only use the provided context if it directly answers the question. These steps reduced hallucinations and made the output more faithful to the evidence. What kinds of metadata are most valuable in contextual retrieval for RAG? Metadata helps retrieval go beyond plain text. Some of the most valuable fields are timestamps, which ensure answers use the most recent information, authorship to weigh expert or official sources higher, and document type, like distinguishing policies from casual notes. In enterprise settings, access-level metadata is also crucial to respect security and permissions. Other useful tags include product versions, locations, or customer IDs, depending on the use case. By leveraging metadata, RAG systems can filter and rank results smarter, making retrieval more accurate and context-aware. Walk us through a technical implementation of context expansion. Start with a normal top K retrieval to get seed chunks, then expand context in controlled steps. 1. Pull each seed's parent section and the immediate previous next chunks to restore local continuity. 2. Run a lightweight entity link extractor on the query and seeds, people, products, IDs, and issue a second retrieval with those enriched terms. 3. Optionally fetch neighbors from a graph or table of cross-refs, e.g., related tickets, version docs. Next, merge and re-rank everything with a cross-encoder or LLM as re-ranker. Drop items below a relevance threshold, deduplicate, and summarize long pieces to fit the prompt. Finally, assemble a clean prompt. Query, brief instructions, compact cited context blocks, guardrails, hard cap on tokens, per source limits, and freshness filters so expansion adds signal, not noise. How do you measure the real benefit of contextual RAG over classic RAG? We measure it by comparing accuracy and usefulness of answers with and without added context. Common ways include human evaluation, judging if answers are more complete, precise, and grounded. Faithfulness scores, checking if the model sticks to retrieved evidence, and task success rates, like whether a customer query is fully resolved. We also track user satisfaction and reduction in follow-up questions. If contextual RAG consistently improves relevance and reduces hallucinations compared to classic RAG, then the extra overhead is worth it. In short, the benefit shows up in higher accuracy and better user trust. What is the overhead or slowdown seen with contextual RAG? And is it worth it? Contextual RAG often adds extra steps, like fetching metadata, expanding context, or re-ranking, which can increase latency by a few hundred milliseconds to a couple of seconds depending on scale. It also increases token usage since more context is added to the prompt. But in many enterprise cases, this overhead is worth it because the answers are more accurate, grounded, and trusted. A slightly slower but correct response is far better than a fast but wrong one. In practice, teams balance this by caching frequent queries and limiting context expansion to high-value tasks. Can you explain how hypothetical responses are generated prior to retrieval? In HyDe RAG, the system first asks the LLM to create a short, hypothetical answer to the query, even before looking at any documents. This isn't shown to the user. It's just a draft that captures the intent of the question. That draft is then turned into embeddings and used to search the knowledge base. Because the hypothetical response is often richer and more detailed than the original query, retrieval becomes more accurate. It helps especially when the query is vague or underspecified, since the model expands it into a more complete form for retrieval. In your experience, does HyDe RAG boost answer quality for creative or technical fields? How? Yes, HyDe RAG is especially helpful in both creative and technical domains. In creative fields like writing or brainstorming, the hypothetical draft expands vague queries into richer ideas, which helps retrieve more inspiring context. In technical fields like coding or medicine, users often ask short or incomplete questions. The hypothetical answer fills in missing details, so retrieval surfaces the most relevant documentation or research. For example, instead of just searching Python API, the draft might be, how do I authenticate with the Python API for cloud storage? Leading to far better results. What evaluation criteria do you use for the hypothetical step? We judge the hypothetical step on three main criteria. First is relevance. Does the draft capture the real intent of the query? Second is coverage. Does it add useful details or keywords that improve retrieval? And third is neutrality. It should not inject false assumptions that could bias the results. In practice, we test by comparing retrieval with and without the hypothetical draft and measure precision and recall of the returned documents. If HyDe consistently pulls more relevant, incomplete evidence without distorting intent, then the hypothetical step is doing its job. How do you handle situations where the idealized answer is vastly different from retrieved reality? This happens in HyDe RAG when the hypothetical draft assumes details that don't match the real documents. If the gap is too wide, retrieval may surface irrelevant results. To handle this, we use a validation step re-rank or filter results based on how closely they match the original user query, not just the draft. Some systems also blend embeddings from both the raw query and the hypothetical answer, so retrieval isn't overly biased. In short, the fix is balancing. Use the hypothetical to enrich retrieval, but keep the original query as the anchor to avoid drifting away from reality. What's a real-life success or failure story from using HyDe? A success story comes from software support. Users often ask vague questions like, "Why is my API failing?" With HyDe, the system first generated a hypothetical error explanation, then used that to retrieve logs and documentation. This consistently pulled the right troubleshooting guides and cut resolution time by half. On the other hand, a failure happened in finance, where a hypothetical draft added wrong assumptions, like assuming a loan product existed when it didn't. That led retrieval toward irrelevant documents. The lesson was to always balance the hypothetical with query grounding and validation. How do you coordinate between the small, fast generator and the verifier model? In speculative RAG, the small model creates quick draft answers, and then the larger verifier model checks or refines them. Coordination is usually done by passing both the draft and the supporting retrieved documents to the verifier. The verifier decides whether to accept, correct, or reject the draft. This setup works well because the small model speeds up response time, while the large model ensures accuracy and grounding. The key is clear handoff rules. Fast generation first, verification second, so the system delivers both speed and trustworthiness. What are common challenges in merging speculative drafts with established facts? The main challenge is conflict. Sometimes a speculative draft adds details that don't appear in the retrieved documents. The verifier then has to decide whether to keep or discard them. Another issue is redundancy, where both the draft and documents repeat the same content, leading to bloated answers. There's also the risk of the draft biasing the final output, even if it's slightly wrong. To fix this, systems use strict grounding rules. Facts must come from retrieved sources and apply re-ranking or filtering to keep the final answer concise and faithful. Can speculative RAG reduce load on expensive models in production? Yes, that's one of its main benefits. The small, fast generator handles the bulk of simple queries and drafts potential answers, which reduces how often the expensive model needs to run full generation. The larger verifier model is only used to confirm or refine those drafts instead of always starting from scratch. This lowers token usage, cuts costs, and improves response times in production. In short, speculative RAG offloads easy work to a cheaper model, while still keeping the safety net of a stronger model for accuracy. What do you watch for to prevent conflicting answers from reaching a user? Conflicting answers usually happen when the speculative draft and the retrieved documents don't align. To prevent this, we put 3 checks in place. First, consistency checks. If a fact isn't supported by retrieved sources, it gets dropped. Second, re-ranking, giving higher weight to evidence-backed content over speculative text. Third, prompt rules telling the verifier model to always ground its final answer in documents, not in the draft alone. Some systems also add citations so users can see where facts come from. These steps ensure the final response is unified, factual, and trustworthy. What industries benefit most from speculative RAG speed? Industries where users expect instant answers benefit the most. For example, in customer service, speculative RAG lets chatbots respond quickly while still being accurate. In finance, traders or analysts can get fast insights from reports without waiting on long processing times. In e-commerce, it helps shoppers get immediate product comparisons or recommendations. Even in healthcare, where speed matters in triage or patient queries, speculative RAG can cut delays while still grounding answers in reliable sources. In short, any field where time to response is critical gains from this approach. Explain the process of integrating retrieval into the model's fine-tuning phase. In RAFT, or Retrieval-Augmented Fine-Tuning, retrieval isn't just bolted on at inference time, it's built into training. The process starts by pairing questions with relevant documents from a knowledge base. These question-document pairs are fed into the model during fine-tuning, so the LLM learns to rely on retrieved context when generating answers. Over time, the model becomes better at using external evidence instead of guessing from memory. This makes responses more grounded and reduces hallucinations. In short, RAFT teaches the model during training to work with retrieval rather than only introducing it later. What indicators signal successful knowledge injection during fine-tuning? Successful knowledge injection shows up in 3 ways. First, improved accuracy on domain-specific benchmarks. If the model answers industry questions better after fine-tuning, it means the retrieval context learning worked. Second, reduced hallucinations. The model leans on provided documents rather than inventing answers. Third, better grounding behavior. Answers explicitly reference retrieved facts instead of vague generalities. You can measure this with faithfulness scores or human evaluation. If all three improve after RAFT, it's a clear signal that the fine-tuning phase successfully injected knowledge into the model's behavior. Have you seen a case where RAFT outperformed retriever-only upgrades? Details? Yes. In one enterprise setting, the team tried improving performance by only upgrading the retriever, better embeddings and re-rankers. While retrieval got sharper, the model still sometimes ignored context or hallucinated. After applying RAFT, where the model was fine-tuned to actually use retrieved evidence, accuracy improved much more. For example, in compliance Q&A, answers went from generic summaries to precise, document-grounded responses. The difference was that RAFT trained the LLM to depend on retrieval during generation, not just rely on it at inference. That deeper integration made outputs both more accurate and more trustworthy. What are the trade-offs in retraining costs with RAFT, and how do you justify them? The main trade-off is cost versus accuracy. Fine-tuning with RAFT requires compute, labeled data, and retraining time, which makes it more expensive than just upgrading a retriever. But the payoff is better grounding, fewer hallucinations, and stronger domain alignment. For enterprises handling high-stakes data, like finance, healthcare, or legal, the cost is justified because errors are far more expensive than the training investment. In lower-stakes settings, retriever-only improvements may be enough. In short, RAFT costs more upfront. But when accuracy and trust really matter, the return on investment is clear. How does fine-tuning retrieval change the evolution of in-domain language models? Fine-tuning retrieval with RAFT shifts how in-domain models are built. Instead of training giant models packed with all possible knowledge, you can keep the base model smaller and rely on retrieval for domain-specific facts. Over time, this makes models more modular. General reasoning stays in the LLM, while fresh or specialized knowledge lives in the retriever. It also encourages continuous learning, since updating the knowledge base improves performance without retraining the whole model. In short, RAFT pushes language models toward being lighter, more adaptive, and tightly integrated with retrieval. What feedback mechanisms drive adaptation in multi-stage pipelines? In multi-stage RAG pipelines, feedback comes from both users and the model itself. User feedback includes ratings, corrections, or clicks on suggested answers, which help tune retrieval and re-ranking. Model feedback can come from confidence scores or self-reflection steps, where the system checks if the retrieved context truly answers the query. Some setups use reinforcement learning, where the pipeline is rewarded when the final output matches ground truth. Together, these feedback loops guide the system to adapt retrieval depth, stage count, or query reformulation, making multi-stage RAG more accurate over time. How do you track and debug at each retrieval stage in these complex systems? Debugging multi-stage RAG means checking every step separately. First, log the queries after each reformulation to see how they evolve. Second, inspect the top documents retrieved at each stage. Are they actually relevant? Third, track re-ranking scores to confirm the best chunks are being promoted. Latency and token usage are also monitored since each stage adds overhead. Some teams build dashboards that show query to retrieval to re-rank to generation, so errors can be traced to the exact step. By breaking it down stage by stage, you can quickly spot where relevance or grounding is lost. Where do you see the future of adaptive RAG beyond text into multimodal and federated scenarios? The future of adaptive RAG is moving well beyond text. In multimodal RAG, systems will retrieve not only documents, but also images, charts, audio, and video, giving richer, more complete answers. For example, a medical assistant could pull both a patient's lab report and an X-ray image to support a diagnosis. In federated scenarios, RAG will be able to query across multiple private knowledge bases securely without centralizing all the data. This is crucial for industries like finance or healthcare, where data can't be shared freely. Together, multimodal and federated RAG will make AI assistants more powerful, collaborative, and trustworthy. How do you balance cost, speed, and accuracy when scaling a RAG system to millions of documents? Balancing cost, speed, and accuracy comes down to smart design choices. For speed, we use approximate nearest neighbor, ANN search, so queries scale quickly across millions of documents. To control cost, we cache frequent queries and pre-compute embeddings so we don't recompute every time. For accuracy, we add re-ranking layers, but only on the top few results to save compute. Often, hybrid search, combining sparse and dense retrieval, also improves efficiency. In practice, the balance is to keep retrieval cheap and fast, while letting the LLM focus only on the most relevant, highest quality chunks. What role does active learning play in continuously improving RAG retrieval quality? Active learning helps RAG systems improve by learning from user feedback. For example, if users upvote or click certain results, the system knows those chunks are more relevant. If they correct or reject answers, those examples can be fed back to retraining the retriever or re-ranker. Over time, the model learns which queries map best to which documents, even in changing domains. This reduces reliance on manual labeling and makes RAG smarter the more it's used. In short, active learning turns user interactions into training signals for better retrieval quality. How do you evaluate trustworthiness in RAG beyond accuracy? For example, transparency and explainability. Trustworthiness in RAG isn't just about accuracy, it's also about showing how the answer was built. We evaluate this by checking if responses cite their sources so users can verify information. We also look at consistency. Does the system give the same answer to similar questions? Another factor is bias detection, making sure retrieval and generation aren't skewed toward limited sources. Finally, transparency dashboards can show what documents were retrieved and why. Together, these measures build confidence that RAG isn't just correct, but also explainable and fair. What architectural differences appear when building RAG for real-time streaming data versus static knowledge bases? With static knowledge bases, documents are indexed once and updated occasionally, so the system focuses on efficient retrieval. With real-time streaming data, like financial news or social feeds, the architecture needs continuous ingestion, re-embedding, and re-indexing. This means pipelines must support low-latency updates and sometimes prioritize freshness over completeness. We also need expiration policies so old data doesn't clutter retrieval. In short, static RAG is batch-oriented, while real-time RAG is continuous, demanding faster indexing and freshness-aware retrieval. How can RAG integrate with agent frameworks to enable reasoning plus action, not just question answering? RAG provides the knowledge, while agents provide reasoning and action. By integrating RAG with agent frameworks, the system can retrieve context, reason over it, and then decide on next steps, like querying an API, writing code, or sending an email. For example, an enterprise copilot could retrieve a policy, explain it to the user, and then automatically draft a compliance report. The integration works by letting the agent call RAG as a tool for grounding, then use its planning logic to act. This moves RAG from just Q and A to being part of full task automation. How can you enforce role-based access control, RBAC, in a RAG pipeline? In RAG, RBAC ensures only authorized users can access certain documents. You enforce it at the retrieval layer by tagging documents with access permissions, then filtering results based on user roles before they are passed to the LLM. For example, HR data might only be retrievable by HR staff. This keeps sensitive content secure while still enabling relevant retrieval. What techniques help ensure compliance with GDPR or HIPAA when using RAG on sensitive data? Compliance comes from combining three things: data minimization, anonymization, and auditability. You only store what's needed, strip out identifiers, and log retrieval requests. For HIPAA, ensure PHI is encrypted and only accessible with proper authorization. For GDPR, also support the right to be forgotten by enabling document deletion from the knowledge base. How do you reduce latency in RAG pipelines for real-time conversational agents? Latency can be cut by caching frequent queries, using approximate nearest neighbor, ANN search and vector databases, and limiting retrieval to smaller top K results. Pre-ranking documents before retrieval also helps. Some systems use lightweight re-rankers first and only call the heavy model if needed. The goal is to keep responses under 1 to 2 seconds. When do you prefer long context LLMs over RAG? And when does retrieval clearly win? Long context LLMs are good when you have a single large document or short-lived context, but they're expensive and still limited. RAG wins when knowledge changes often, when data is too large to fit into a prompt, or when you need fact grounding from external sources. In practice, many systems blend both. How do you evaluate RAG in open domain settings where ground truth answers may not exist? In open domains, exact answers may not be known, so we evaluate on proxy metrics, relevance of retrieved docs, factuality of responses, and user satisfaction. Retrieval can be judged with precision and recall, while generated output can be checked for hallucinations or consistency. Human evaluation often complements automated metrics. What's the role of human-in-the-loop evaluation versus automated metrics in RAG? Automated metrics like precision or BLU give scale but miss nuance. Human-in-the-loop evaluation is critical for checking trust, usability, and edge cases. A hybrid approach works best. Use automated scoring for bulk testing, but validate quality and safety through periodic human review. What challenges arise when moving RAG from prototype to production at enterprise scale? The main challenges are scaling retrieval across millions of docs, keeping knowledge bases fresh, ensuring low latency, and enforcing security policies. Prototypes often ignore governance, but in production you need monitoring, version control of embeddings, and explainability for business trust. Which orchestration frameworks, LangChain, Llama Index, Semantic Kernel, etc., best support RAG, and why? LangChain is popular for modular pipelines and fast prototyping. Llama Index is strong for document indexing and flexible retrieval strategies. Semantic Kernel integrates well with Microsoft ecosystems and enterprise tools. The choice depends on your environment. Research projects lean to LangChain. Enterprise use often favors Semantic Kernel. How is Retrieval-Augmented Editing, RAE, different from RAG, and where is it useful? RAG retrieves documents to help generate answers. RAE goes a step further. It uses retrieval not just for generation, but for editing or rewriting content. For example, updating outdated documentation with retrieved facts. It's useful in content management, where documents must be dynamically corrected instead of just summarized. Could large context LLMs eventually replace RAG, or will they complement each other? Large context LLMs can reduce the need for retrieval in some cases, but they don't solve data freshness or private data access. RAG ensures answers are grounded in external sources, which long context alone can't guarantee. So instead of replacing each other, they will complement. LLMs handle broad context, RAG ensures accuracy and up-to-date facts. You've just explored the 110th most important RAG interview questions, from classic pipelines to adaptive architectures. Mastering these concepts isn't just about clearing interviews. It's about preparing for the future where AI systems don't just retrieve information, but reason, act, and collaborate. And that's where we're heading next. In the next session, we'll dive deep into AI agents and agentic AI systems. The systems that move beyond answering to planning, taking actions, and working with tools. If RAG is about knowledge, agents are about intelligence in motion. So stay tuned, subscribe, and join me in the journey to mastering the future of AI.